In this video, we will state and prove the results we were alluding to while discussing examples in the last video. The theorem can be stated as if V is a finite dimensional vector space and L is a linear map from V to W, then range of L is a finite dimensional subspace of W. And dimension of V is equal to dimension of the null space of L plus the dimension of the range of L. Now, we give a name for the dimension of range of L. It is called the rank of the linear map. Similarly, we give a name for the dimension of the null space. It's called nullity. Therefore, we can restate this as dimension of V is equal to the sum of nullity and rank. And therefore, this theorem is often called rank nullity theorem. Now, part of this theorem is easy to see and we kind of implicitly used it already while discussing the examples in the last section. This is the statement that range of L is a finite dimensional subspace of W. The basic idea was that if you take a basis V1, V2, V3, etc. up to Vn of V, then the vectors L of V1, L of V2, etc. up to L of Vn spans the range of L. And therefore, range of L is finite dimensional. This was the basic idea. Of course, we did not prove it, but we kind of used it when we discussed the examples. And we will prove it rigorously when we are proving this theorem. However, the issue is that these vectors need not be linearly independent. In fact, in the worst case, it can so happen that one of these vectors is equal to 0. When will this happen? If one of the vectors V1, V2, V3, etc. up to Vn belongs to the null space, then one of these vectors will be equal to 0. Therefore, we have to avoid vectors in the null space. Therefore, we have to construct a basis of V in a smart way and use that basis to prove this theorem. That is the basic idea. But before going to the proof of the theorem, let us understand this theorem using the two examples that we had seen in the last video. The first example that we saw in the previous video was not that interesting. This is because, as you would recall, the null space of this function was the singleton set 0. So all we get is that the range of f has dimension 2, which is the dimension of the domain. This is not so interesting as we already saw that range of f is the span of the two vectors f of 1, 0 and f of 0, 1. Therefore, all we know from the rank nullity theorem in this case would be that these two vectors have to be linearly independent. So that's all we get from the rank nullity theorem. Of course, we did not rigorously prove that range of f is the span of these two vectors, but let us look at a quick proof of it now. Notice that any vector in R2 is of the form x, y. And any x, y can be written as x into 1, 0 plus y into 0, 1. Therefore, f of x, y is equal to f of x into 1, 0 plus y into 0, 1. But by linearity, this is equal to x into f of 1, 0 plus y into f of 0, 1. Therefore, any vector in the range can be written as a linear combination of f of 1, 0 and f of 0, 1. And thus, range of f is indeed the span of these two vectors. Now let us try to see why these two vectors have to be linearly independent. Recall that that is the consequence of the rank nullity theorem in this example. So proving this is proving rank nullity theorem for this special example, correct? So let us try to prove that they are linearly independent. So let A and B be two scalars such that A into f of 1 comma 0 plus B into f of 0 comma 1 is equal to 0. But by linearity, A into f of 1 comma 0 plus B into f of 0 comma 1 is equal to f of A into 1 comma 0 plus B into 0 comma 1, which is equal to f of A comma B. So this implies that f of A comma B is equal to 0. But as the null space is the singleton set 0, this implies that A comma B is the 0 vector. So you get 0 comma 0. A comma B is equal to 0 comma 0. Which means that the vectors f of 1 comma 0 and f of 0 comma 1 are linearly independent. And thus we proved the rank nullity theorem for this special case. Now let us go to the second example. The second example is a bit more interesting, and this example will illustrate some of the ideas in the proof of the rank nullity theorem. So let us go through it a bit more carefully. Recall that the null space was equal to the set of all x comma minus x comma 0, where x is a real number. And we had also noted that this set is nothing but the span of a single vector 1 comma minus 1 comma 0. And we also saw that this function is a surjective map. In other words, the range of f is equal to R2. Therefore, notice that the null space has dimension 1 and the range has dimension 2. Therefore, the dimension of R3, which is 3, is equal to the dimension of null space plus dimension of range of f. And thus, we have verified the rank nullity theorem for this particular example. But let us dig a bit deeper and understand this better by going through the sketch of the proof that I was mentioning earlier. As I said earlier, the basic idea is to construct a good basis of R3. And how will we do it? We will first take a basis of the null space. In this case, it's just a single vector 1 comma minus 1 comma 0, and we will extend this to a basis of R3. For instance, I can take the two additional vectors 1 comma 0 comma 0 and 0 comma 0 comma 1. This is an extension of the basis of the null space to a basis of R3. Now notice that if you look at the images of these three vectors, those three vectors will span range of f, or in other words will span R2. However, the image of this vector is the 0 vector and therefore is uninteresting. So what is happening is the images of these two vectors itself will span the range of f. In other words, this vector spans the null space and these vectors spans the range of f, and all these vectors together span R3. And this is exactly the reason why the dimension of R3 is equal to the dimension of the null space plus the dimension of the range of f. But before concluding, let us see why the images of these two vectors spans range of f. To see this, notice that under f, these three vectors are mapped to the vectors 0, 0, 1, 0 and 0, 1. And clearly the two vectors 1, 0 and 0, 1 span R2, which is equal to range of f. So in this fashion, we have understood the rank nullity theorem for these two examples. And this basic idea that we saw in this example can be generalized to a proof that works for all cases. Let us now look at that proof. To prove the theorem, as we did in the example, we will start with the basis u1, u2, u3, etc. up to um of the null space of L and extend this to a basis of the vector space V. Let this basis be equal to u1 to um, comma w1 to wn. Now notice that as this forms a basis, every vector v can be written as a1 u1 plus etc. up to am um plus b1 w1 plus etc. up to bn wn. And the range of L contains all elements of the form L of V. But linearity implies that we can write this as a1 into L of u1 plus etc. up to am into L of um plus b1 into L of w1 plus etc. up to bn into L of wn. Now notice that as u1, u2, etc. up to um belongs to the null space, L of u1 is equal to 0, L of u2 is equal to 0, and so on up to L of um is equal to 0. Therefore, L of v can be written as b1 L of w1 plus etc. up to bn L of wn. In other words, the vector L of v is a linear combination of the vectors L of w1, L of w2, etc. up to L of wn. And this is true for any vector v. Therefore, we can see that range of L is equal to span of L of w1, L of w2, etc. up to L of wn. If we show that these vectors L of w1, L of w2, etc. up to L of wn are linearly independent, then we will see that these vectors form a basis of range of L, which would imply that the rank of L is equal to n and the nullity of L is equal to m. And we already saw that the dimension of V is equal to m plus n, which is equal to the nullity of L plus the rank of L. And that would complete the proof. So all we need to prove now is that the vectors L of w1, L of w2, etc. up to L of wn are linearly independent. Let us prove that next. To show that L of w1, L of w2, etc. up to L of wn are linearly independent, assume that constants c1 to cn are such that c1 into L of w1 plus etc. up to cn into L of wn is equal to the 0 vector. Now, by linearity, this is equal to L of c1 w1 plus etc. up to cn wn. But the fact that L of this vector c1 w1 plus etc. up to cn wn is equal to 0 implies that c1 w1 plus etc. up to cn wn belongs to the null space of L. But we know that u1, u2, etc. up to um form a basis for the null space of L. Therefore, we can write the vector c1 w1 plus etc. up to cn wn as a linear combination of the vectors u1 to um. In other words, we can rewrite c1 w1 plus etc. up to cn wn as d1 u1 plus etc. up to dm um. But this implies that minus d1 into u1 plus etc. up to minus dm into um plus c1 w1 plus etc. up to cn wn is the 0 vector. But the linear independence of the vectors u1 to um, w1 to wn implies that all these constants are equal to 0. In particular, the tuple c1, c2, etc. up to cn is equal to the 0 tuple. which means that the vectors L of W1, L of W2, etc. up to L of Wn are linearly independent. And this completes the proof of the theorem.